Namaskar my dear friends. Let us see a DC converter high efficiency buck converters. So this buck converter is going to solve for many solutions like HART modems, automations or DCAs. Okay. Basically what happens is we have very high input at the input side and we need very low output voltage, let's say 3.3 volt or 5 volt with very low current, let's say around 60 milliampere or something like that, because these are used in like sensor applications. So let me first tell you the applications. Basically, let us say you have 4 milliamperes to 20 milliamperes some loop powered systems or HART modems. Basically, it is also called as highway addressable remote transducers. Okay, we have a lot of building automations these days like video calling, audio calling, sensors, temperature sensor measurements, proximity sensors, all those things are there. We have distributed power supplies which requires a lot of sensors technologies and communications. We have industrial control supplies as well. So in this all, and we have like distributed control systems or SCADA systems where a lot of sensor technologies are used. Okay, so basically they need a very low current source, let's say 60 milliampere or 40 milliamperes with a voltage range of around 3.3 volt to let's say like 5 volt or something like that. Even it can I mean the IC what I'm going to discuss can give you very high voltage output. Okay, that's not a problem. So we are going to see this particular IC which is ADP2360. This is going to be one of the best IC for this kind of applications. Another so many other manufacturers are also there like Texas Instruments is there, then Renesas is there. We have monolithic power systems, but analog devices is kind of like quite I mean high precision and very premium device. That's the reason I always prefer analog devices for this particular applications. Okay, coming back to the like details about this particular IC, we have, you can see it has 50 milliampere, 60 volt it can give you output. Okay, or in 60 volt it can take input. Okay, maximum. The high efficiency buck regulator. This is the product data page, like product page that is there, and this is the data sheet. So I'll just open it for you. This is the product page which you can see all the details. We have application circuit, we have like the pin configurations and all these things. If you click here you will get your product data sheet. Okay, and we have features and everything that is mentioned. We'll do one by one, and at the same time we have evaluation board as well for this. So let us discuss this particular like IC, and at the same time we will make use of this particular IC to our various applications that we have studied, which we are going to utilize them. Okay, mainly I have used this particular IC for various applications in our like building automations as well as DCS, distributed control systems designs. Okay, and one of the application was there in HART modem as well. Let's talk about the simple design that we have here. As you can see, this is the typical circuit that is shown in the diagram here. So we have input voltage. So generally we have input voltage around, let's say 24 volt or 12 volt. Okay, it can take up to 60 volt, that you remember. Okay, but generally I have used for 24 volt input and 12 volt inputs. Even for 5 volt input it can be used to give you 3.3 volt output, or up to 5 volt also it can give you for separate applications. We just need one input capacitor, one output capacitor, and one inductor selections, and one current like limiting resistor. Like you have to set a current so that it will be easy for you. Let's say you can set up to like 60 milliampere current, but you don't need more than 20, so you will set it to 20 milliampere current only. Okay, you don't need more than 20. Then we have soft start like IC pin as well as we have enable pin. Okay, and they have already designed one evaluation board for us so that we can like evaluate this particular IC as well as make use of this IC in our applications. So first of we'll see this application design, like how we can design it for our applications, or to suit to our particular applications in our design. Before that, we'll try to move to understand what are the different features and its IC parameters. Okay, So if you talk about the features, as I already mentioned, this can take up to 4.5 volt to 60 volt inputs, and it can give you adjustable range output up to 0.8 volt to V input. V input means it can give you as high as 60 volt output also. Okay, or let's say if you have 12 volt input, it can give you up to 12 volt output with 100% duty cycle. Okay, so this is what this IC is capable of. It has a fixed output voltage options also with 3.3 volt and 5 volt ranges, and it can give you current up to 50 milliamperes of current, and there is a adjustable peak inductor limit which can set up to 140 milliampere of. So basically what happens is your I max, which is going to be less than or equal to half of I peak. Okay, so I peak will set 140, then it will give you maximum 70 milliamperes of current, like that it will be set up. Then it is pulse frequency modulation control. It has very high efficiency, like it can give you up to 90% of efficiency for 9 volt input and V output of 3.3 volt. Similar to that, it can give you 87% of efficiency if you are going to take I output of around 1 milliamperes. So sometimes it happens like you design it for 10 milliamperes, but you are not drawing 10 amperes, 10 milliamperes, you are drawing let's say 2 milliampere or something, just for one sensor application. In that case you don't need a lot of current. There are a lot of sensors these days. We have ambient temperature sensors, we have pressure sensors, and we have like light emitting diodes, and all those things are there. It has very low shutdown current, it has very low quiescent current, and then it can work up to 100% duty cycle that I told you. It has under voltage lockout method also. If you want to make sure that the IC doesn't give you the output before a certain voltage level has reached, let's say this level, then only it will start, then that time you can set it for under voltage lockout also, but there is no other requirement as such. No external component will be needed. We have enable input pin for precision threshold control, and we have a programmable soft start as well by using one resistor. We have power good output, like it can indicate that the output is within the range, and it is having thermal shutdown protection as well. It is very small package with 8 lead LFCSP package. Okay. Coming back to absolute maximum rating. So absolute maximum rating, you have to make sure that all the voltage applied to the pins or taking away from the pin must be within the range, otherwise the IC may damage. So this is the very important parameter that we always need to look into while designing any of the circuit related to either switching regulator or linear regulator or any other IC that you take care of in your electronic circuit design. So basically we have V input, enable pin, power good, analog ground and power ground, so they can take up to 61 volt, and feedback pin can take up to 5.5 volt. We have SW pin that is going to give you the output which is going to get connected to the inductor. Okay, so this SW pin will be taking up to V in plus 0.3 volt, it is going to give you output of this much maximum. Okay. We have ITH soft start. We have this thing can take up to 4 volt, and the temperature range can be up to 125 degree centigrade, and soldering condition is JDDC J standard of 0 to 0. Okay, let's talk about the IC. So once we see this IC is 8 pin package. Okay, and we have the pins, let's say enable pin, power good pin, ITH pin, which is going to be current programming pin. So enable pin, it has to be used as a enable threshold, so you have to give one high output here, a high input here, so that it can get enabled. Okay, power good indicator is going to give you a power voltage set is let's say 3.3 volt, then it will give you a power good indication as high from let's say 3.1 volt to 3. Let's say 7 volt. Okay, so like this the power good indicator works. Okay, we have ITH pin which can help us to adjust the I peak current limitation, okay, in the inductor, and also it will give you an understanding of how much current you can draw from the output. Okay, FB pin is actually used for your feedback control pin, where you have to attach one resistor feedback divider, so that it can give you the desired output what you want at the SW pin. This is not input, this is actually the output is at set pin. Okay, rest other pins are always there, like we have SW pin, which is switch node pin, which will be getting connected to the inductor, and we have input pin, which is going to get the input voltage. Okay, and we have power ground, which is going to have the driver connection ground, and we have AGND analog ground, and exposed pair ground is also there, which must be connected to the ground plane. Okay, let us talk about the block diagram. So in block diagram, as you can see, we have two kinds of IC. One is fixed, and one is adjustable. So rest all other pins we have already discussed. Let's say a V input pin, we have to give the input voltage here, and with one bypass capacitor. Similar to that, we have SW pin, which is going to get connected to the inductor and plus output capacitor to give you the output voltage. We have power ground here, PGND, and similar to that we have uh, power good indicator, which is going to get connected to V input. If you do not want to connect it to V input, you can connect it to separate 3.3 volt that is there in your system if it is available. Okay, so that it can be supplied to the microcontroller to for status checking. Okay, this enable pin you can connect it here, so that it makes this particular IC enabled, and this voltage must be more than V enable rising, which is a threshold voltage of around 1 volt. Okay, we have soft start capacitor, which will be required to make a soft start output, so that it gives you a smooth rise of output voltage. There will not be any a spike or something or ringing at the output of the start time, right? And we have ITH pin, which is going to set the inductor peak current, so that your inductor is not going to get saturated or something like that. Now very important thing is we have adjustable output range and we have fixed one. So fixed one, you can see directly you can take the out feedback pin to connect it to output, and internally the resistor feedback dividers are connected. Okay, but in adjustable range we have to connect a separate resistor feedback divider, so that you can set your output voltage to this particular pin. Okay, so if you talk about typical application, let us say we have fixed version. Let me just make it bigger. Okay, so fixed version, what I'll suggest always is keep, let's say scene, let's say 10 microfarad plus one more capacitor, you keep it. Okay, 0.1 microfarad, it will be easy for you. Otherwise, if you want, you can increase this particular capacitance to let's say 22 microfarad as well. And let us say we have a 24 volt input, then keep an understanding that the voltage rating of the input capacitor must be minimum 2 times or something like that. It will be easy for you. Okay, so keep it, let's say 50 volt rating or something like that. If you have 12 volt input, then like 35 volt will do, or even 25 volt will do. Okay, so this is how you have to understand. So input capacitor is done. We have the power good indication. So power good indication can be taken. If you want, you can connect it to pull up with V input itself, and then take it with a voltage divider again. Okay, here, and this pin we can send it to MCU pin. Okay, so this is how you can downgrade this particular voltage. Let's say it is 12 volt, then downgrade it to here, let's say 3.3 volt, and so that MCU pin can keep a monitor on this particular power good indicator. Okay, otherwise you can do one more thing. This particular pin can be pulled out with 3.3 volt directly if it is there in your system, and this is how you will be able to make sure directly it can get connected to my MCU GPIO. Okay, we have enable pin. If you want, you can directly connect it to like V input, so that there is no need of like disabling enabling. Or otherwise, if you want to reduce the current consumption at the system level, then you can send a microcontroller signal high, so that it can get switched on. Rest others we have already explained. You can keep a soft start, let's say 0.1 microfarad or something like that. There is a calculation that I will tell you, and similar to that we have ITH calculation as well. The thing what I want to tell you here is L, if you want to use for very high frequency application, then you can go ahead with 100 microhenry. By default it will work, no problem will be there at the V output. Okay, but the suggestion is always like, let's go ahead with 330 microhenry, or let's say 470 microhenry. Okay, maximum you can go ahead with 600 microhenry, but that is not needed. You can go with these two values, that is more than enough for your high efficiency design of your any output voltage. Okay, and we can put C output same way, like let's say 10 microfarad, we have 3.3 volt, then 10 microfarad of 16 volt will do, even 10 volt will do. Okay, try to keep one more 0.1 microfarad capacitor for smoothing output or something like that, so that it will be easy for you. Okay, similar to that, this was like fixed version. So this is the going to be adjustable version. Only one change that you will be required to do is you have to connect one feedback resistor like RFB1 and RFB2, so that it can help you to set the output voltage based on this particular calculation. And same way, C input, C output, you can make changes to keep yourself, and we have a feed forward capacitor that will be required to make output stabilized. Okay, coming back to the calculation of feedback resistor. So once we know like how to calculate the feedback resistor, it will be easy to set the voltage output. So let's say we have voltage output of 3.3 volt. Anyway, 3.3 volt we have already fixed version, so you can utilize that. Even if you do not want to use, then you can go ahead with adjustable version and set V output to 3.3 by using these two resistor combinations. And let us say RFB falling is set to 0.8 volt, that you have to understand. And then let's say RFB1 you are going to set let's say 10 kilo ohm. Then accordingly RFB2 you can calculate based on this particular formula, so that it will be calculated. Okay, coming back to peak inductor setting. Okay, so what happens is the current setting for current. Okay, for current. So if you keep this particular pin open, then I peak will be set to 50 milliamperes. If you keep it 1500 kilo ohm, then it will be set to 60 kilo ohms. Okay, if you keep it short circuited, then it will be set to maximum current, which is going to be 140 kilo ohm. Okay, so I have always set set my output current to around 287 kilo ohm to make it 120 milliamperes. Okay, so that it can give me an output current of 120 by 2, that is 60 milliamperes of current. Okay, similar to that, for lower application you can set it to 1.5 mega ohm, that is 1500 kilo ohm, to give you output of 60, that is 60 by 2 is going to give you 30 milliampere. So this is how you can set it. By default, if you want to keep it open, then it will give you maximum 25 milliamperes of current at the output. Okay, basically the output current is less than half of I peak current going through the inductor. Okay, so it will give you 30 milliampere maximum or even lesser than that. Okay, as I already mentioned, the inductor selection, so you can go ahead with 100 microhenry to 600 microhenry, otherwise 330 microhenry or 470 microhenry are more than enough for your highest efficiency applications. Okay, and if you want to order this particular component, you can go ahead with these versions. Like this is my adjustable version, which is going to be ADP 2360 ACPZ-R7, and this is going to give you an adjustable version of whatever voltage you need. Okay, similar to that, for 3.3 volt fixed and 5 volt fixed, these two part numbers are there, which is applicable. Okay, rest all are fine. So hope you have understood this particular high efficiency DC-DC converter with very low current output, and the output voltage setting is very precise. And there are various applications to this particular ICs, like as I already mentioned, for building automation generally it is used, or HART modems. Okay, so any kind of applications in like industrial control supplies or distributed power supplies is there in your automation or factory automations or somewhere, where generally it is required for sensor applications, where you need to have a separate power supplies. Even if in your PCB you have 3.3 volt available, but you don't want to power the sensor with that particular supplies because of mixing the signals, then you can utilize this one of the best IC for your particular application to your sensor power supply. Okay, so if you do have any questions or any specific queries regarding this particular uh, particular kind of applications, or if you need to choose a particular switching regulators for very high input but output is very low, let's say 3.3 volt with very low current, then you can put down your queries in the comment box and we shall be able to answer you out with your best chosen IC. And what are the different methods that we should follow? That is the most important thing. First of all, it's not only suggesting the IC by us, we are actually building you to understand how you can become an independent engineer on your own for various like application design or any kind of problems that is occurring in your like projects or something like that. Okay, thank you so much.